So let's go to the next behavior. Let's take clustering because I had started with that. The clustering, of course, I'll just repeat it that you've got different robots and they need to cluster out. And I think we've already discussed this behavior, so let me draw it up, and that will be all. Now, if you naively implement that up, it will not make one cluster, it will make multiple clusters of red, multiple clusters of blue, and multiple clusters of black, and therefore you need to have the same thing, random behavior and an artificial potential field. So randomization is always my mantra at a local level. So that's after t time, and this is with probability p, with probability 1 minus p. And there you go, that lets you do the clustering. We talked a bit about the bird flocking, so that's what the behavior is. These are the birds, they don't look like one. Believe me, these are. And say they want to go over here, which is a goal. Sometimes there's no goal, so let's do it without goal. Now here, this behavior relies on something that students do a lot that's called as centrality. And that says every robot attempts to maintain the same orientation as its neighbors. So let's give in random orientations before I do this one. So let's consider this robot. So the neighbors are, I can only typically not look at back. So let's say effectively the neighbors become these. So I'll take the average of this plus this plus this plus this divided by 4, which will, it appears, turn out to be pretty much what it is currently. This. So I'll change my orientation to here. Now the birds can actually look around, they can look around and get this kind of an orientation from different ones. Now there are two exceptions to this, so that's my basic behavior. Every robot attempts to maintain the same orientation as its neighbors. So neighbors, same orientation. Now, unfortunately, it's not collision aware, so let's make it collision aware. Two close robots repel. So these are too close, so they will repel. It might actually still go here because the robots will not be able to make a sudden turn. And a robot too far off is attracted to the closest robot. So for this, the closest robot is here, what it can see. It'll try to go here, but then of course there are kinematic constraints, it won't be able to go here. And this, the closest robot is this, so it'll try to go here, of course it will not be able to go. If you have a goal as well, along with this 1, 2, 3, now and basically it's a selection algorithm. This is the basic behavior, but then you select this behavior or this behavior on exceptional conditions, too close and too far. Too far, if you maintain an orientation, you know what will happen. You'll keep going away. So things have to be a function of distance as well, not just the orientation. And too close, you'll actually collide. If you have a goal, just add a new intent, a new behavior, a new force, which is attraction to goal, and take a weighted addition from between attraction to goal and orienting as compared to your neighbors. That's all. So this is what is the collective motion. It's actually an interesting behavior. This is actually how you walk in malls, walk in traffic, walk in educational institutes. So each one of you tries to go centrally as compared to all others. Believe me, many times in malls, some of your friends don't even know where are you going. You decided the favorite restaurant. They don't know what is the favorite restaurant. So they're just trying to take central tendency. Many times there are two ways that reach CC3. Some of your friends don't even know which way will you follow. They just take central tendency. So some of the agents feel attraction to goal, the others just have a central tendency behavior. Of course, you avoid going too close to each other and you avoid going far away from each other. Sometimes all of them know and therefore there's attraction to goal for all of them. And sometimes what happens is that obstacle will come around over here. So of course, this is just the attraction part of it. The repulsion from obstacles is still there. That's why you simulate it up, you'll see that everybody will split, form two subgroups, and then again merge. That's something beautiful. So that's how most of you actually navigate. So at the local level, I just have a centrality over here. Of course, followed by attraction to goal if available and a mandatory repulsion from the obstacles. Let's move on to one of the most interesting behaviors that I have over here. So slowly we are just maybe increasing the tempo up a little bit. And let me write it down over here. So we've got goal seeking. Now it may appear that we've already done goal speed seeking, so why are we doing that again? It's already done. And therefore let me just change in the goal seeking. It is goal seeking for a special robot which is not a part of the swarm. So let's have a complex scenario now. So now we really have mazes. In fact, let me put in complex mazes. And let me really complexify it up. And there's a robot over here that needs to go from this, which is a source, all the way up over here, which is the goal. Now we know that this is the path. A-star algorithm, you would have been able to find that out, but then you cannot use the A-star algorithm. Motion planning techniques and other codes, you would have been able to find out now, but then you cannot use that. So I say that there are many swarms. There's a swarm of many robots. And this is what the initial distribution is. So what I do is I first invoke dispersion. And that's a behavior already studied. This robot is all the way up over here. It's not participating. So I'll of course do it quickly. The dispersion behavior is going to result in this. The number of robots may not match. Now I say that, of course, it's a wireless ad hoc network, so every robot actually sends a signal to the others, and if the signal is intercepted by the obstacle, they cannot communicate, but if the signal is not intercepted by the obstacle, they can communicate. Either send light, absolutely no problem, or send any signal which will get decepted by obstacles. Sometimes using the actual strength as well, you can take signals similar to Wi-Fi, which can actually get attenuated by obstacles and so on. And this robot is still here. So this is what is the ad hoc network. So taking an example, these two robots had their light beam or whatever beam you were using intercepted by the obstacle, so they could not commute, and these two could commute because there was no obstacle in between them. Now what you do is that the goal, of course, is something which is special, and that sends a special signal. So I say the goal is something special that sends a special signal. So I add the goal over here like this. Now, all these robots, they now communicate as a wireless ad hoc network. So everyone has an emitter through which digital packets are sent, and it has a receiver through which digital packets are obtained. So suppose we are doing for this robot over here or the robot U, and it's connected as an ad hoc network to so this gets, let's call it U, let's call it V1, let's call it V2, let's call it V3. This sends distance from the goal of V1 in terms of number of hops. This sends the distance from goal in terms of number of hops for V2, and this sends distance from goal in terms of number of hops to V3. What U does is it calculates distance in terms of number of hops of U in terms of whatever is the minimum that it has received as distance to goal. Of course, it will be for this one. V2 will have the minimum, which will be 1, 2, 3, 4, 5, 6, 7. And its distance is distance from of goal from here plus one more hop. And I need not say that because you already know this. It is exactly the same algorithm that you would have looked into the wireless literatures. Now, the interesting thing is it's still a graph search. So it's the same BFS formula. This is BFS. However, it's completely distributed. So this one is also known as a distributed BFS. Breadth first search is the algorithm where there's one queue, you put everything into that queue, you take out a node, you calculate distance of its children, you add the children up into the queue again, you again take out something, calculate the distance you through it of its children, put the children into the queue. When you take out the goal, you're like, okay, I got it. This one is a distributed BFS. There's no single queue. So every vertex is a processing unit. It takes distance from the goal from everyone. It adds one, and which is the same BFS formula, and it transmits itself. So I receive d of vi from all nodes, and I transmit d of u. And then, of course, if you do it for this one will receive this d of u, this d of u, this d of u, and the minimum one will be from this plus one. So it's a bit for search, so the path is not optimal. Because the edges are unweighted in a BFS, the path would have been optimal if I would have taken a weighted graph, or I would have taken a uniform cost search or a Dijkstra's algorithm where the edge weights are concerned. This is unweighted, so it's not optimal, but then it's good enough. So that's the second stage. So the first stage is dispersion. The second stage is a distributed BFS. Now you come to the same thing that I said in the fusion of deliberative and reactive algorithm. So there's another wireless ad hoc network that this makes from all this. So it will always be connected to the neighbors as long as the signals don't intercept. So it queries these two. What is the distance of goal from you? What is the distance of goal for you? So let's take this as the robot queue. So robot queue is also connected to, so I should have written VI as neighbors of you. Okay, so this queries this one and this one. What's your this number of hops to goal? What's your number of hops to goal? Okay, yours is smaller, so I'll take you as a goal. So Q is attracted to VI that reports least distance to goal, which basically means same thing. VI is argmin dgvi, where VI is dynamic neighbors. Now, of course, distributed DFS is a lot faster than distributed BFS is a lot faster than BFS, provided all these are physical nodes, and it's fast because it's parallel. Secondly, distributed BFS is, of course, adaptive. It can adapt to change of map. So if I insert an obstacle over here, then automatically, okay, here no alternate path is possible. So if I add this path, if I add an obstacle over here, this connection will get broken, and automatically the shortest path will adapt to this one. So distributed BFS is faster because of parallelism. Distributed BFS is adaptive. BFS is not. It cannot handle change of map. But then it's only because all these are physical nodes. And therefore, let me just do this thing quickly. So I take this one as the goal. Let me actually write down the distance of goal in terms of number of hops for all of them here. So it's 1 over here, 1 over here. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 9, 10, 11. You can actually verify that this formula will always be true. And that's exactly how I'm calculating. So for any node, look at all the neighbors and you'll have least is 10 plus 1, 11. So this queries which is the smallest, 11. So the robot starts going towards 11, but as soon as it's over here, it makes a connection with this, and then 10 says I'm better than 11, so it goes around over here. As soon as it comes here, it's still, now it makes a connection. It's actually repelling, it's physical robot, so the repulsion is all active. Now it makes a connection with 9, and 9 says I'm still better, so it goes here. Then it comes into contact with 8. 8 says I'm still better. So it's a greedy agent, it's going towards the least numbers. Now it comes into contact with 7. 7 says you're following 8. If you follow me, I'm 7. Wonderful. Then it comes into contact with 6. 6 says you're following 7. If you come to me, it's better than 5, 4, 3. Here it's actually interesting. Here it comes into direct contact with 2. So after 5 and then 4, it actually goes to 2 and then 1. And then, of course, goal is 0. So it directly goes to goal. It will have to avoid all this because, of course, there are ultrasonic sensors and repulsion from obstacles is always there. And the large number of nodes don't bother me because these are extremely low cost devices. So the cost doesn't matter to me. So that's a pretty interesting behavior. So let's just write this thing down. So this one was stage 3, which is robot navigation. And these robots are extremely small. So if you just walk outside my room, you'll see big corridors because they were made for fat people like me. And you know, all the fat people who sit outside my office, these robots are very small. So you could have hundreds of them fit in a row. It's just shown larger in terms of size for different reason.